That's so sad.
Okay, folks, we can get started. Numbers feel a little sparse today. Something going on campus? It's one of those days, maybe?
Cold out.
Cold out. So my plan for today is to go through the process by which I recommend you get your controller tuned in order to actually balance the inverted pendulum. Make sure I'm recording. Which again is a recommended process. It's one that I think you'll find helpful. Once we get through that content, we will have talked about all of the content that's really of direct relevance to Lab 3. And then after having talked about this, my plan for the subsequent lectures is to spend as much time as folks would find useful talking through any bugs that might exist and trying to get this thing balanced. And then after that, to start getting into some sort of special topics that folks might find useful for final projects. So into material that isn't of direct and immediate relevance to lab assignments, but is of general relevance for folks as they start working on final projects. So to that end, if there are any topics that folks would like to hear about, let me know and we'll do a lecture about those things. Some topics that occur to me as perhaps relevant might be, I think I'll do a talk on the power management system on the RP2040. So suppose that you have some sort of an IoT flavored project where you care deeply about battery longevity and you're trying to reduce the power consumption of your system. I want to talk about how you can do that using the CSDK and talk through the various control registers for controlling those things. I think today I'm going to talk about, we've talked about DC motors to some extent and the internal mechanisms inside DC motors. I want to talk about some other flavors of actuators today because folks might find some different kinds of actuators useful for their final projects. In particular, I want to talk about servos, something that you're probably familiar with, but I'll talk about them in a little bit more detail than perhaps you've seen. I want to talk about stepper motors. When is it appropriate to use a servo? When does maybe a stepper make more sense? And then some other flavors of actuators that, depending on what you're doing, you might find useful. And then other topics that folks might want to hear about, I'm open to suggestion. Maybe a talk about electrodes. People would find that interesting. How do you sort of outfit your own arm, for instance, with electrodes in order to detect finger movements? I saw a couple project proposals in that direction. The project proposals look great, incidentally, the ones that I've seen so far. And then after that, it's whatever folks want to talk about. If you want to talk about radio stuff, if anyone's thinking radios, we can talk about that. I'll come up with a list and we'll start moving through that list. And then the other thing that you can expect in the not too distant future is, as I explained on the first day of this whole course, my whole role in this course is to help you build each lab assignment and then ultimately to help you build your final projects. And for most of the semester, one of the best ways that I can help you guys do that is in these lectures. I can go over content that is of relevance to the labs and to your final projects. At some point, however, it usually becomes the case that the way I can be most helpful is to be in lab more. So at some point in the next 2 weeks, 3 weeks perhaps, what we'll likely do is stop meeting here for lectures and instead I'll be in the lab for these hours and folks can come in and get some additional lab time with me and with your TAs to work on your final projects. Usually it's the case that that's the way that the course staff can be of the most help to you all at the end of the semester. Okay, and that'll happen whenever it makes sense. If there's a certain list of topics that folks would like to get through, we'll take as much time as we need in order to get through that stuff, and then we'll transition over to extra lab time. Yeah?
How else will the lab hours change during the final project?
How will the lab hours change during the final project?
Will there be additional lab hours, or will it just be...
Yeah, so all of the lab sections will remain what they are. And then in addition to those, the lab sections as they exist presently, all the lecture times will become additional lab time. And I know that you can all make that time because you're all here. Right? So we'll have additional lab time by substituting the lecture hours. And then I will continue doing what I've been doing, which is essentially just opening up the door of the lab in the morning. Sometimes I forget to do that, by the way. And if you are going to work in the lab in the morning and it's not open, just come knock on my door and I'm happy to open it up. Generally speaking, as long as there's not another class in Phillips 238, I'm very happy to open up the lab so that folks can go in there and work. I won't necessarily be in there all the time. I'll kind of be popping in and out. But I will be in the lab for all the dedicated lab sections, plus the lecture hours, plus some additional time on Mondays and Tuesdays. And then it'll be open for you all to work essentially whenever there isn't another class in there. 2300 specifically. Okay, any questions? Yeah.
I have a new idea for my project.
Okay, what is it?
I just came up like 5 minutes ago. So can I make some sort of like a Game Boy stuff? You can make a screen and has some buttons and 3D print a case. You can play your own mini game with it.
I think that'd be a fantastic project. Yeah, so a little sort of Game Boy-esque video game console.
Yeah.
Yeah, video games in general, they make really nice final projects because you are playing them as you build them. So there's a lot of just sort of implicit incentive to optimize because you want for the game to be more fun because you're making the game. So video games as final projects tend to be very successful for that reason because you want, you know, there's always additional bells and whistles that the creator wants to add.
And you know those, like you have your like portable consoles, you have like pads in it, and you can interact with other people's consoles so that like, you can compete.
Okay.
So you maybe use your Pico W to do that wireless.
Sure. So I think, as I mentioned last time, a nice thing to do for these final projects is set up a series of milestones. That maybe, you know, you have some reach milestones involving that, but you know, if you were to start with just an individual single player game on some sort of little console, and then as a reach goal extend that to interacting with other devices, I think that's totally reasonable.
Yeah, because it's cool to have, it's not just like a Game Boy, it's like having personal console, like cyber consoles.
Sure, yeah, I think that'd be great. Any other questions about final projects from folks? Okay, there's something else that occurred to me when you asked that question, but I can't remember what it was. It's okay, it'll come back to me. So interrupt me at any time if you want to talk about final project stuff or more specific Lab 3 things. But otherwise, I want to start talking through the last bit of content that's going to be of relevance to you for Lab 3. And in particular, that is tuning the reaction wheel PID controller. And let me just say that tuning a PID controller, there are methods for doing this that are, what's the word? This is pretty experimental, you know, change something, see what it does, change something, see what it does. There are methods for generating PID controller gains that are a little bit more rigorous and that put you in a reasonable ballpark from which you then further tune. This is going to be a little bit sort of seat of the pants PID controller tuning, right? Which for a class like this, I feel like that's okay. But what I want to walk through is the order in which you might consider tuning this PID controller so that you can debug as you go. Because it's one of these things that it can be a little bit tricky to get it tuned, particularly for a system like this, unless you're following some sort of a systematic procedure, right? That where you can understand, I'm changing this controller gain, this is the difference in behavior that I expect to see, do I see it, yes or no, and then I move on to the next thing. So the first thing to get implemented for your PID controller is something that all of you have at this point already gotten implemented, which is the complementary filter. So the complementary filter, I'll just very briefly remind you, this is our filter that is taking as input the pendulum arm angle as estimated by the accelerometer alone, and the accelerometer angle as estimated by the gyroscope alone, and synthesizing the two into an estimate for the arm tilt angle that is better than you can get from either the accelerometer or the gyroscope alone. And the output of that complementary filter, unless you change it to different units, but if you use the setup that's described on the complementary filter webpage, that output will be in degrees in a fixed point representation. So your complementary filter is giving you an angle in degrees. What you will then do is compare. So, and as that's implemented, does anybody remember, is straight up 0 degrees or 90 degrees? I can't remember the convention that's used in the write-up. I think it's 0. I think it's 0, yeah. So you know, it could be whatever it is. You just make sure, you have to make sure you're consistent. But I believe that as sort of written up, 0 degrees is straight up, which is to say that 0 degrees is your desired angle for the pendulum. So what you will then do, that all lives right now in your interrupt service routine. So right now your interrupt service routine probably looks something like clear the interrupt flag, gather a batch of measurements, compute the complementary angle, maybe signal to your VGA thread to draw that angle, and then exit. And this week, what we'll be doing is adding more stuff to the interrupt service routine after the computation of the complementary angle. The first thing that we'll add is a calculation of the angle error, which is to say the difference between your estimated angle from the complementary filter, where is the arm right now, as measured by the sensors, compared to our desired tilt angle, which is 0 degrees, right? So the complementary filter, maybe you go through this process and it says we are currently at 1.5 degrees. The next computation that you'll do is you'll say my error angle, my angle error, whatever you want to call it, or just error, my error is my desired angle, 0 degrees, minus my current angle as estimated by the complementary filter. So suppose the complementary filter told us that we were at 1.5 degrees. Our error in this case would be minus 1.5 degrees, 0 minus 1.5. That error is the input to the PID controller. And what the PID controller will do is take this error in units of degrees probably, and it will convert it to a control input to your motor, which will be in units of, you know, it's going to be a duty cycle to the PWM channel. So it's going to be probably some integer in the range of minus 5,000 to plus 5,000, assuming that you've kept the wrap value for your PWM channels at 5,000. And remembering, incidentally, that a duty cycle is always a positive value. So all that the plus minus is telling you is which of the two PWM channels are we assigning the duty cycle to, and which one are we zeroing. So in any case, we go through and we compute this error. And then the first term of the PID controller that I recommend you implement is just the proportional gain, the P part of the PID controller. PID stands for proportional integral derivative. The proportional term of the PID controller, all that it does to compute a duty cycle is scale that error in degrees by some constant that we'll call Kp, the proportional gain. Right? So say this is minus 1.5 degrees, maybe we scale that by 1,000 or something, so that the duty cycle that we then compute associated with that particular error would be, you know, minus 1.5 times 1,000, 1,500 or so. And, you know, this Kp, this is an example of one of the parameters that you'll be tuning. You'll be, you know, changing it until you get the behavior that you want out of your system. What's a reasonable value to start? And, you know, you might ask yourself, a way that you might come up with this angle is to say, okay, what's the range of angles over which I want for my controller to operate? Maybe it's plus minus 3 or 4 degrees or so. And you could say, okay, I want for my motor to be fully on in one direction or the other direction when it's at the outer limit of that range of angles, 3 or 4 degrees. So I'll set my Kp value to, you know, something in the range of 1,500 or so, just as a place to start. So that if I'm at the furthest extreme of where I can recover the arm, it's spinning as fast as it possibly can, right? And then of course, if it's at 0 degrees, this error will be 0 and our proportional input to the PID controller will be 0. How do you see if that's working right? Well, what I recommend is you hold the arm in your fingers and you sort of move it back and forth. And on the VGA screen, what you'll have displayed is the complementary filter output, which is showing you what is the current arm angle as estimated by the complementary filter. And then also displayed in real time on the VGA screen will be the output of your PID controller, which at this point will just include the P part, the proportional term. And what you should see is you tilt it one direction, and as the error increases, you should see the controller make the wheel spin faster and faster in one direction. You pull it back the other direction. As it goes through vertical, it should slow to 0 speed. And then as you tilt it in the opposite direction, it should spin in the opposite direction. And something to notice and to try to feel as you do this is if you move this back and forth, as you move it through 0, does it feel like the arm is trying to stop itself around 0? Or does it feel like you get through 0 and it tries to pull itself over? If it tries to pull itself over, you have a sign error, right? And the fix is just switch the sign on KP, right? Easy enough. But it's just something to look out for is notice what it feels like as you move this arm around. Does it feel like it's trying to catch itself at 0, or does it feel like it's trying to pull itself down to the ground? We can't balance this system with just a proportional gain. It won't work. Suppose our proportional gain were too low. Or suppose that it were on the low end, right? Maybe our proportional gain was, I don't know, something on the order of 100. The effect of that, if we tried to balance this, would be, suppose we start it straight up. We're not going to be able to balance it. It'll start to tip over a little bit. As it tips, the proportional gain will notice that difference between where we are and where we want to be, and it'll start to increase the motor speed. If KP is too low, the wheel will slowly ramp up in speed. But remember that torque is dl dt. It's change in angular momentum, right? So if it spins up slowly, you're not getting much torque out, and this thing's just going to continue to fall right over. So what you will see with a low KP value is this starts to tilt, it spins a little bit, and then just falls over. Which reminds me, by the way, something that's not actually written up in the lab assignment, but what you might consider implementing is if you detect that you are at an angle that is outside the range that you're trying to control, maybe you're at 5 degrees or something, you could just zero the PWM duty cycles to turn off the motor, just so that it's not screaming away when it tilts over.
Because it saturates when it's outside the range?
Yeah. If you have KP really high, then this tilts just a little bit. Suppose you have it really, really high. This tilts just a little bit. All of a sudden, your duty cycle goes to some incredibly high value, and this thing starts spinning really fast. It accelerates very quickly from not spinning to spinning. It's going to pop back across. It'll spin really quickly in the other direction, and probably what you'll see is it maybe bounces back and forth a few times, getting further and further from center each time it bounces, and then it tips over. And by the way, for this week's checkout, this is what I'm hoping to see. At least proportional control. It's a good idea to get as far as you can with the other elements of this controller this week, because that gives you a lot of time next week to get it tuned. But all that I'm expecting to see is closed loop control. Just proportional is fine, right? But I want to see closed loop control of the motor. The next addition that I recommend you make to the PID controller is to add integral control. So the proportional part of the PID controller is just looking at and scaling the instantaneous difference between measured angle and desired angle. Where am I right now? Where do I want to be? What's the difference? Scale it, that becomes a duty cycle. The integrator part of the PID controller does something different. What it does is every single time we enter that interrupt service routine to compute, to gather a new batch of measurements, compute our angle again, compute a new PID controller gain, it increments some separate variable, which maybe you call error accumulation, by the instantaneous error. So if you were to grab the motor and hold it over here off of center, this would increase by the amount by which you've moved it off of center every single time you enter the interrupt service routine, 1,000 times a second in our case, since we're running this at a kilohertz. And then what the integral part of the PID controller does is scale that accumulated error. Remembering, incidentally, that error could be positive or negative, right? If we are consistently for many cycles on one side of the vertical, then this will increment positive, positive, positive. It'll get bigger and bigger and bigger. Alternatively, if we're on the other side, it gets smaller and smaller and smaller. So the P part of the PID controller is looking at the instantaneous difference of where we are and where we want to be. The I part is looking not only at the instantaneous difference between where we are and where we want to be, but also includes information about our past error. And I recommend, incidentally, that you have some checks here where you say, if this accumulating error exceeds some threshold, that's another tunable parameter. You can decide what that threshold is. But I would start with maybe, half of the max duty cycle or so. So if the maximum value that your controller can output is, say, 5,000, just to say fully on motor, maybe you start with an Imax of like 2,500 or so. And you say, in the event that this error accumulation exceeds that threshold, just set it equal to the threshold. Alternatively, if it's less than the opposite of that threshold, set it equal to that threshold. Why do that? Anyone read the PID controller webpage? This is to prevent a problem called integrator windup, where you could imagine that if we, say we were off of center for a while, so that error accumulation term kept accumulating and accumulating and accumulating and got very, very large. When we came back to the other side and started decrementing it, it would take a long time for it to actually come back down to zero. So the consequence of this would be, if we held the wheel off of center for a while and then let go, well, the physics of that wouldn't be the same as some other systems. But essentially, it prevents for the error accumulation to grow without bound beyond a level where it can be sort of corrected on timescales that are appropriate for the controller that we're working on. Just to give you an example of this is a different system, but for this system, the system that's being controlled is there's a little drone motor on the end of a lever arm that's connected to a potentiometer here to measure angle. And what this is trying to do is control the drone arm up to hover at 90 degrees. But I'm holding the arm down here with my foot, and I don't have that accumulator clamp set up, so I'm not preventing integrator windup. And so the effect of this is that error accumulation gets bigger and bigger and bigger and bigger, and when I finally let go of the wheel, it just slams right past the desired angle, right? If instead we clamp the maximum that the error accumulation can get, then when we let go, it overshoots a bit, but it hasn't grown to such a value that it can't correct itself. The I part of the PID controller for this system is really important for getting it to balance. Because suppose that we are off by just a little bit and the wheel wants to start tipping over. It's the I part that will accumulate that small amount of error quickly to speed the wheel up and correct it. This part of what makes this particular control problem challenging and interesting is what really matters here is the rate of change of the wheel speed. Not the wheel speed. The wheel speed doesn't actually matter. The speed of the wheel isn't what is exerting torque. It's the rate of change of the wheel speed. The I part of the PID controller is what changes the rate of the wheel speed when we have a small error, when we're off by just a little bit. It speeds the wheel up in the correct direction to pop it back up to the correct orientation. Do you agree with that, Bruce? Okay. The physics of this system is actually kind of tricky and interesting. Okay, so what will your controller look like when you just have proportional and the P part and the I part of your PID controller implemented? I think that what you'll find is that it does something like this, where perhaps it balances for a little bit, and then what you may see is that the wheel starts to spin in one direction. Maybe it corrects itself once, and then it just increases and increases and increases and tips over. And the reason for this is if it's off by just a little bit, just a tiny little bit, it takes quite a bit of time for that to actually, the physics of this system, that tiny error, in order for that to start to become a large error and tip over, it takes a bit of time. But in the meantime, the I part of our PID controller is incrementing that error accumulation relatively slowly. So the wheel is spinning up relatively slowly, not fast enough to actually correct the system, but fast enough to start to saturate the controller. So that by the time this starts to tip over meaningfully, more quickly that is to say, our wheel is already nearly saturated and it doesn't have any more to give. It's already spinning at full speed. So probably with just P and I implemented, I expect that that's what you may see. I expect that probably what you'll see is you start with it approximately balanced. Maybe it tips a little bit and corrects itself. And then probably what you'll see is it will speed up and continue to increase its wheel speed and then tip. So that's a problem to solve. The way that I recommend solving that problem is to add, let me see here, add integral control, is to add a little bit of dithering, which is to say, you set some other parameter that we'll call angle increment, some small number. Maybe it's like 0.0001 degrees, or maybe it's a little bit bigger than that, right? But it's some small number. The units of this, incidentally, is degrees, right? Some small amount of degrees. And what we do is we look at the instantaneous error, the sign of the instantaneous error. Are we on the left side or the right side of the vertical? And whichever side that we're on, what we do every time through the control loop is, if we're slightly on, say, this side of the vertical, we set our desired angle such that it runs away from our present angle at a relatively slow rate. So instead of always controlling the arm to directly vertical, what we do instead is move our desired angle to somewhere close to vertical, but somewhere that it moves a little bit as a function of where the arm actually is, so that our desired angle is always running away from our present angle at a speed that you control by setting this angle increment value, right? You set this too high, of course it's not going to work. You set it too low, say you set it to 0, the effect that you'll see is the one that we just looked at, where this wheel will likely spin up and then tip over. But if you play with this a bit, what this will do is, say you're off by just a little bit, it moves your desired angle over to increase the error a little bit more quickly than it otherwise would, so that your integral part of your PID controller speeds the wheel up quickly enough to pop it back up to its correct orientation. It'll pop it back up past where it's supposed to be, and then the same thing happens in the opposite direction. And so what you'll see is that it sort of bounces around gently the vertical. There are other strategies that you might do to mitigate this, but this one I find works pretty well. Yeah?
Just to make sure, our desired angle is always 0, right?
Yes, yes.
You like tested it or changed it?
It won't hover off of the vertical because gravity's introducing a torque then. It will do so for a small amount of time. But since gravity's introducing a torque, we need to be exerting a torque in the opposite direction to hold it there. The only place the torque comes from in this system is speeding up the wheel. As soon as we saturate the motor, we've lost control and the thing falls. Other questions? And then this snippet of code here also includes the last term of the PID controller, which is the D part, the derivative part. So the proportional term is looking at the instantaneous angle. The I term is looking at the integral of the angle, some history of the angle over the past, number of cycles. The derivative term is looking at the derivative of the angle. How quickly is the angle changing? The derivative term sort of fights back in some sense against the proportional and the integral term, right? So you could imagine that suppose we're tipped off from center a little bit. The proportional term and the integral term are both trying to move us back up towards center. And the higher you make those gains, the more responsive your controller. It does so more quickly, more responsively, but you are introducing instability when you do that. You will have a tendency to overshoot and overcorrect, and then the thing will fall over. It'll do so more quickly, right? But you're adding instability when you increase your P gain and your I gain. What the D part of the PID controller does is, if it notices that the error between where we are and where we want to be is decreasing quickly, which is to say, we were off by a little bit, the proportional and integral terms here are really slamming us back up towards vertical, like so fast that we're probably going to overshoot. The derivative term slows the system down. So it works in the opposite sign, SIGN, as the P term and the I term, so that if it notices, hey, the error is decreasing really quickly, it slows the motor down. Same thing in the opposite direction too. If it notices that the error is increasing really quickly, it helps speed the motor up to catch the arm. So this is with proportional and integral control with dithering, so there's no D here yet. And what you'll see is that it balances, but it's not very robust. Just to say, if I smack it with a pencil, it tends to fall over. I think actually this just falls over on its own after a while. It balances for a little bit, but then controller saturates. As soon as the controller saturates, we've lost control, and the system falls over. Should happen in a second. And now this includes the derivative term. And the system is much more robust. The other tuning that I've done here is, if you look carefully when this slows down, you'll see some screws sticking out the side here. There are holes the whole way around this that will accommodate 1032 screws so that you can increase the mass of your wheel a little bit. Right? That increases the angular momentum of the wheel, so it gives you more sort of torque back and forth. But with proportional and integral and derivative and with some dithering, the balancing behavior is much more robust. It's robust enough to withstand, smacks with pencils and stuff. And what's interesting to keep an eye on is the top trace back here is the control input. And when I smack it again, watch what happens to the control trace. It's hard to see, but you can see it snaps up and then corrects itself. So when I smacked it this direction, I moved the arm this direction, and the PID controller changed the control input in order to catch it. There, it caught it again. So when we test your final system, we're not going to sit here for an hour and see if the thing balances for an hour. But what I will ask for you to do is turn the system on, get it to start balancing itself, and we'll watch it for like a minute. And we'll just see if it stays balanced. And then we'll smack it with a pencil. And we'll see the extent to which it can reject those sort of impulse disturbances, right? It can only take so much, right? We don't ask too much of these things. I'm saying a pencil because they're relatively light. So you'll hold a pencil loose and smack it. It can withstand those sorts of things. If you were to come in and like hit it with a water bottle, it's gonna fall over, right? So we're gonna see if it can balance itself, and we're gonna see if it can withstand relatively minor impulse disturbances. Yeah.
You have to check that the duty cycle is still less than 5,000 before you update it.
Yes.
Otherwise, you just keep it at maximum.
Yes, that's right. Yep. This is a challenge. I thought I thought it would be nice, for the last lab here to do a good challenging thing. Getting this thing to balance is hard, in part because, if you remember from physics, the longer this pendulum arm is, the easier it is to balance. You probably have experience of this just from like daily life. If you ever try to balance like a baseball bat or a golf club or something, it's pretty easy actually. If you try to balance a pencil on your hand, it's perhaps impossible. Maybe some of you can do it, but the speed of the control that's required in order to balance a pencil is way greater than the speed that's required to balance something like a baseball bat or a golf club. This is pretty short. So getting this to balance is not easy. Okay. Any other questions about this? So let me just summarize. My recommendation, once you've got the complementary filter running, is to first implement proportional control. And then you take your arm with your proportional controller implemented, you move it gently back and forth. You should see the controller responding to the instantaneous position of the arm. And as you move it through vertical, you should feel the arm kind of try to catch itself. If instead you feel that the arm is trying to pull itself in the direction that you're moving it, then you have a sign error, right? So just something to keep an eye on. Once you have proportional control working, I then recommend that you add the integral part of the PID controller. And what you'll likely see in that case is the arm does an okay job, maybe for a little bit, maybe one or two corrections balancing itself, but then probably what you'll see is it'll get off by just a little bit. The wheel will start spinning up faster and faster and faster, but not fast enough to actually correct itself, not accelerating fast enough to actually correct itself, and it'll tip over. Then I recommend you add dithering, which is moving your desired angle a little bit each time into the interrupt so that your desired angle is always running away from your measured angle. And I expect that what you'll see then is an arm that balances, but maybe for 10 to 15 seconds. And when you smack it with a pencil, it probably falls over. And then I recommend you add derivative control and see how robust you can make the controller. And the game that you're going to be playing is increasing KP and KI, which allows you to catch yourself more quickly, and then increasing D a little bit, which prevents you from overshooting and increases stability, right? So you're trading these things off. And the other things that you might be playing with, so things that you will be tuning include KP, KI, KD, I max, which is the maximum value that your error accumulation can achieve. You can tune that as well. And that angle increment. How fast does your desired angle run away from your currently measured angle? You can tune that as well. Yeah.
So do all those values, like, will we all have the same exact values for like same KP, same KI, or like within a range? Are there multiple like answers to this?
It's a good question. There is no right answer for these values. I expect that everyone's values will probably be of the same order of magnitude, but what those values are depends on a lot. It depends on the specific characteristics of your motor as opposed to someone else's motor. There's going to be variations there. So I expect that everyone's values will be different, but of approximately the same order of magnitude. And incidentally, the other thing that I'll mention is, I mentioned that with the proportional gain, the heuristic that we were using to give ourselves just a reasonable starting guess was to say, okay, when I'm at like 4 degrees, I want the P term to be fully on. Keep in mind that the I term of the PID controller is looking at the integral of the error. That integral of the error is going to be perhaps several orders of magnitude larger than the instantaneous error, because we're adding up the instantaneous error over and over and over again, so it's growing in size. So for that reason, your KI, the I part of your PID controller, you can expect to be several orders of magnitude smaller than KP. Because we want for the proportional part and the integral part to be, of approximately the same order of magnitude importance to the controller. So KI will be several orders of magnitude smaller than KP. because the quantity that Ki is scaling is several orders of magnitude larger than the quantity that Kp is scaling. And then likewise, the derivative term is working on the quantity that the derivative part of the PID controller is scaling is the change in angle, or the change in error rather. What's the difference between my error this time step and what my error was in the last time step? So that is going to be probably an order of magnitude or several orders of magnitude smaller than the instantaneous error. So you can expect for your KD term, your derivative gain to be several orders of magnitude larger than your proportional gain. And for all of those, I have some recommended values for you to start, right? But that's why you'll notice these differences in order of magnitude for Kp, Ki, and Kd. The values that they're scaling are orders of magnitude different. We want for their contribution to the control output to be, we don't want for one to dominate the others. We want for all of them to be important. Yeah.
Why don't you need like a cascading PID for this? Like, why can you go straight from like why don't you have to go to like desired acceleration to desired position? Like, how can you go straight to desired position?
So is the question, something along the lines, I'm trying to make sure I understand the question properly. Is it something like, why are we not doing torque control?
I guess I'm confused like how PIDs work. So can you just say like there's like a general error and then now this is like the desired motor output? So like, yeah, I guess like how would it change if you wanted to like move the wheel to a certain position rather than like, oh, I'm spinning the wheel at a certain acceleration to get a certain angle?
I see. So if instead of controlling the wheel speed, we were instead controlling the wheel position?
Just be like, go to this position.
Yeah, can you just always do that?
In order to do that,
Say, go to that position.
so there are systems that do things like this, like servo motors, for instance, right? They control, the interior of a servo motor is a DC motor, and we're doing position control of that DC motor. If we wanted to control the position of the wheel as opposed to the speed of the wheel, the things that would have to change, if I get this wrong, folks can correct me, but our sensing would have to change. We would have to measure the current position of the wheel and compare that to our desired position of the wheel. So what does that sensor look like? Maybe it's a potentiometer to which the wheel is attached so we can see what's the current position of the wheel. Maybe it's something like an encoder where we know the position of the wheel. And then our mechanism for controlling the motor would probably have to change a bit as well to allow for us to control, to move it to a specific position. Incidentally, that's kind of how a servo works, right? So a servo motor, inside of it, it has a DC motor. We tell the servo a particular position that we would like to have the shaft of that DC motor oriented in. We encode that position as a duty cycle of a pulse train. But okay, so we're just telling it a particular position to which we would like for it to move. We use some sort of a sensor, maybe it's an encoder, maybe it's a potentiometer, to measure the current position of the motor shaft. We compare that to the position where we would like to be, look at the difference. That goes into a controller that does something similar that we were just talking about, but it's looking at the error between where we are and where we would want to be, and it's converting that error into a voltage that's applied to an H bridge, which moves the DC motor. And then the objective here, what this feedback system will do is drive the measured position of the DC motor to the desired position, or in other words, it tries to drive this error to 0. So here's our servo, right? Here's our DC motor. Our DC motor is probably in a lot of these servos attached to a gear train that goes from the high speed, low torque output of a DC motor to a lower speed, higher torque output of the whole servo. This output shaft is attached to a potentiometer, which is measuring its current position. That goes into a controller, which converts the error between the current position and the desired position into a control input to the H bridge, which then moves the DC motor. What controller is it?
What controller you implement?
So the input to the controller is going to be the it's the position error, so it's going to be some measure of where we are as measured by the potentiometer versus where we would like to be as encoded by the duty cycle of a pulse train. And then that controller converts the error into a control signal to the H bridge, which is actually responsible for moving the DC motor. So most DC, you can get servo motors that are different than this, but suppose some of you took mechatronics, right, or 3400 or something. I believe the wheels that control those robots are servos that have been modified such that instead of controlling the servo to a particular position, you instead control the rate of the servo in one direction or the other. You can modify, a servo of this construction such that you're doing speed control instead of position control by taking it apart and changing a few things. By looking at this diagram and looking at this block diagram, how would you do that? It's kind of a fun thing to do, incidentally. So the way that you could go about doing this is you open up the servo motor, you find this potentiometer, and you twist it to the orientation that's associated with the motor being about halfway through its range of motion, the position out. Say a servo can swing through about 180 degrees. You position this potentiometer to wherever it is at about 90 degrees, halfway through its range of motion. Then you cut this wire so that your potentiometer is always sensing the motor to be at 90 degrees. And then if you say, I would like for the motor to please move to 180 degrees, you encode that position in the pulse train, it's always going to be comparing your desired angle to a static value on the potentiometer that you set with your finger or with a screwdriver, so that this just turns the motor forever in a particular direction towards the desired angle. But because you've cut this line, the turning motor never actually changes the position of the potentiometer, so it just runs forever in the particular direction you want for it to go. You say go to 0 degrees, it runs in the opposite direction. You say go to 45 degrees, it runs in the same direction but more slowly. The other modification you might have to make, by the way, is it's often the case that one of these gears has a rotation stop on it, so you may have to take this thing apart and snip the little rotation stop off the gear and then put the whole gear train back together. On high-end servos, these gears are going to be some kind of metal. On most of the servos that you all have probably worked with, this is plastic, right? Something to remember, by the way, what do all these gears do? It's a gear reduction, so it's converting a high-speed, low-torque DC motor output to a relatively high-torque, low-speed output of the servo. What happens if you take one of these servos and grab the little tip and go
It breaks.
You're putting a lot of you're putting a lot of torque on this side of this gear train, which gets amplified the whole way through here. You're probably going to destroy the gears, probably. This is a really common failure mode for servos in sophomore level classes. There's something weirdly tempting about going like that, but yeah, try to avoid that temptation. Same goes incidentally for the DC motors that we're using in the pendulum lab. There is a gear reduction on those. So if you grab your wheel and go, you could blow out the gear reduction. Okay, we're out of time. That took longer than I expected. That's okay. So I will be in lab in like 15 minutes, and then this evening.
So
I don't understand how some work